Welcome to the Explainer. You know, if you're verifying complex digital designs, relying on a random testing alone is kind of like flying blind right into a hurricane. Sure, you might be generating millions of inputs, but you have zero proof you're actually hitting those critical edge cases. Today, we're fixing that. We are going to explore the ultimate verification checklist by building a practical tutorial on functional coverage within the Universal Verification Methodology, or UVM.
All right, here's our game plan for today. We'll start with the verification hole problem. Look at the building blocks of coverage, define bins and crosses, check out the UVM Coverage API, move into sampling and collection, and finally, wrap it all up with achieving coverage closure.
Let's dive right into part one, the verification hole problem.
So here is the million-dollar question in hardware design. How do you actually know what you haven't tested? UVM gives us these incredibly powerful tools, right? Like constrained random stimulus generation. But honestly, using that without tracking is like throwing darts blindfolded. You might throw a million, maybe even a billion darts into your device under test, but unless you take off that blindfold, do you really know if you hit the bullseye? How do you know your randomizer didn't completely skip over a critical protocol state?
And that is exactly where functional coverage comes in. Think of this as your ultimate verification checklist. It brilliantly separates the act of driving the stimulus from the act of actually proving what was tested. So rather than just crossing our fingers and hoping our randomized darts hit everything, functional coverage actively measures which specific design features and scenarios were successfully exercised. It's how we find and ultimately eliminate those dangerous verification holes.
Okay, moving on to part two, building blocks of coverage.
Let's look at a practical example straight from our sources, a PCI transaction cover group. In SystemVerilog, a cover group is the main container for your coverage model. You can think of it as the master architectural blueprint that holds absolutely everything we want to track for a specific interface or protocol. Now inside this blueprint, we define specific line items, and we call these cover points. A cover point looks at a highly specific variable in our transaction state. So, in our PCI example, we've got address CP actively monitoring the transaction address and type CP keeping a close eye on the transaction type. These are the specific individual items ticking off our master checklist. Which brings us to part three, defining bins and crosses. So, cover points are great, but we really need to get granular here, and we do that by defining bins within them. Looking at our address cover point, we don't just want to know if any address was hit, we want to know exactly which ones. By explicitly defining practical data bins, like a low range, a mid-range, and a high range, we literally force the simulator to track which specific address chunks were hit. And here's the kicker. If a bin stays empty, that is a massive clue. We instantly know that specific range was completely ignored by our tests.
Now, tracking individual variables is a fantastic start. But let's be real, the most devastating bugs almost always hide in the messy intersections of different states. And that is exactly where cross-coverage steps in. By writing something like cross-address_CP, type_CP, we force the tool to prove that every single address range was tested alongside every single transaction type. It's a total game changer. It multiplies our verification confidence exponentially because it guarantees all those tricky combinations are actually tested together.
All right, section 4, the UVM Coverage API. Let's shift gears from SystemVerilog syntax and look at how the Universal Verification Methodology actually manages all this under the hood. Straight from the UVM class reference manual, we look at the register abstraction layer. Kicking things off is basically a two-step handshake with the UVM framework. First up, we use include coverage to tell the system which model should be included. Then, we use build coverage to tell our UVM components exactly which of those coverage models need to be actively constructed. But here's the thing. Just building it isn't enough. The framework doesn't just start collecting data automatically. If it did, it would totally tank your simulation performance. So, we have to flip the master switch in the control room. We must explicitly call set_coverage. This is the function that actually turns on the collection of those functional coverage measurements for our blocks and memories. Once you flip that switch, boom, the UVM infrastructure is officially listening. This leads us perfectly into part 5, sampling and collection. So, the infrastructure is built, the master switch is on, now we reach the moment of truth in our test bench, actually capturing the data. The trigger point for this is the sample method. According to the UVM spec, this method gets invoked by the register abstraction class whenever an address map is successfully read or written. The second that transaction happens, sample fires dynamically, and it securely logs our data right into those specific bins and crosses we mapped out in our blueprint.
To quickly summarize this essential methodology checklist, number 1, you specify and build it using include and build coverage. Number 2, you explicitly enable it using set coverage. And number 3, the environment actively triggers sample to dynamically capture the data. If you miss even one of these sequential steps, you simply aren't going to get the data you need.
Finally, let's wrap up with Section 6, Achieving Coverage Closure. We take all that data generated by our sampling and we output a coverage report. As our source tutorial perfectly puts it, coverage data reveals verification holes, addresses, or scenarios never exercised by stimulus. Let me tell you, reviewing one of these reports is a pretty visceral experience. You'll be scrolling through this massive wall of 100% full green bins, and then, suddenly, you spot it. One glaring empty red box. That empty bin is a massive red flag. It instantly shows you a specific scenario your random stimulus completely missed, pointing you exactly to where a nasty bug could be hiding. But when every single bin finally turns green, that is when you know you've achieved coverage closure. So, you're now armed with the anatomy of SystemVerilog cover groups, the extreme granularity of bins and crosses, and the specific UVM register API required to build, set, and sample your data. The real question is, how will you use this methodology to bulletproof your next chip design? By implementing functional coverage systematically, you literally transform verification from a stressful guessing game into a mathematical certainty. Thanks so much for joining me on this explainer, and hey,